the day 19 solution broadcast. So as you can see here, we still have another hour and a little bit to go before problem 20 becomes available, but I just wanted to chime in with, and colored lights on the tree, that's nice. I just wanted to chime in with the solution that I ended up with for day 19. And this, so the solution itself ended up being pretty small. So I completely, I started basically from scratch here and defined. So, all right, this might take a little bit of an explanation, but basically, so I quit for the night last night, but then I couldn't sleep, and the reason was that I kept imagining how I might solve this problem, and what the conclusion that I ended up coming to is that while it was hard for me to predict, like way in advance, which elves would be stealing, which elf would have their presents stolen, it was very easy for me to predict the first few elves that would have their presents stolen. And a way of thinking about that is, and it might be like a little bit nicer. Maybe I can pop a quick diagram in here. But if the elves are kind of sat in a circle that looks like this, then it's very easy to figure out who the first 4 elves are going to steal from, because 1 will steal from 5, and then 2 will steal from 6. Okay, that much is obvious. Then when you get to 3, what happens is 3 has to skip 7. And the reason that 3 skips 7 is that basically because we've removed these 2 elves here, that the sort of the balance of the rest of the elves has shifted more towards 3's right. So 3 steals from 8, and then 4 steals from 1, like that. And then if we were going to keep going, if there was another elf here, then it would skip another one. And then by the time you get to 7, then it becomes pretty confusing again. But the general rule for taking for the first half of the elves is pretty easy to figure out who they're going to take from. And if you run an algorithm on that gets the right answer for that advances you basically halfway, then you can sort of call that same algorithm again, and what you end up with is an algorithm with performance n log n. So this is that implementation there, and all the work is sort of being done in this calculation right here. So basically we're saying, all right, for the first half of the elves that are on the table, we're going to basically take where the elf is, let's see, add, so this is that sort of aspect where every 2 elves we're going to skip somebody. And then here, this is just the count. So this is just in order to give us our offset into, like in this case, say 5. And then what we get by way of demonstration, let's see. So if we, let's just do this. So here you can see that we start with 1, 2, 3, 4, 5. Then we end up with 4, 1, 2. Which means, elf 4 is next to come, then elf 1, then elf 2. Then after you run this, 4 stealing from 1, so then you end up with 2, 4. And then in the last iteration of this, you end up with just 2 by himself. And then that's just what this algorithm is doing here. We're just saying keep running your 1 round. So basically you're going to start by cutting your input in half, then you're going to cut that in half, and so on. So I'm timing each of these 1 rounds, and then you can see how this behavior has the effect of the first. When it's running over an array of size 3 million, it takes a few seconds to actually finish running. In this case, 7.3 seconds. But then the next time through, it takes about half as long. Then the next time through, half as long again, and then eventually it converges basically, and then gives us this answer here, who is the last elf standing. So that ended up being that ended up being the answer, and I was able to get it this way. I took a quick look at some other approaches that people took, and they said actually that I actually heard about folks that had inefficient algorithms, but that they noticed some kind of pattern here. So if I let's see if I can very quickly try to like figure out what sort of pattern this is. So this is elves 1 through 10, and then let's see, elves 1 through 100, elves 1 through 1,000, 10,000. Yeah, not exactly clear what's going on here. Maybe if we look at it one at a time. Oh, hang on a sec. Oh, this is actually, all right. So interesting. So yeah, it looks like, at least to a certain extent, it seems like increasing this by 1. You know what we could do is we could say like, well, so on 100, it does seem like this number is sort of always increasing. Yeah, it does look like there's some sort of pattern there. I don't immediately see what it is. But I guess that this is sort of a problem that's been explored before, and a number of folks in the challenge were able to figure out, were able to quickly identify that it was an example of that. Yeah, it seems like yeah, it seems kind of like it's going to be a little bit less than half, maybe. Yeah. So yeah, like I said, only just sort of glanced at existing solutions, but this is the solution that I came up with, and it ended up running pretty quickly. Yeah, about glancing back up here. Yeah, about 10. Yeah, about maybe 15 seconds. So not too bad. All right, that's just my update for problem 19. See, got our advent calendar looking good here, and about an hour before problem 20. So I will see you then. Thanks for watching.